Ladies and gentlemen, boys and girls, welcome to the Structural MD Podcast, Episode 9, Fused Deposition Modeling. So I really got to get an introduction down for the show besides introducing it like it's a circus. I think I might end up doing that throughout all these episodes. I'm not sure, but I definitely got to think of something a little bit more professional for you guys. After all, this is a attempt to be a professional show. Anyway, today we're going to cover fused deposition modeling. Now this is probably the most popular consumer printing process. It's just the cheapest when compared to stereolithography, which is, I guess you could call a competitor. However, it's kind of slanted. A lot more people use fused deposition modeling over stereolithography just because, like we mentioned, stereolithography has a lot of quirks, and I am going to do an episode in the future where I kind of compare the two from a consumer standpoint. But stereolithography has a lot of quirks when it comes to that vat of liquid. Storing it in certain temperatures, keeping it out of sunlight, using gloves to handle it. You can only use it like 3 or 4 times. The vat container that holds the liquid is a consumable. You can't keep it for a long time, etc., etc., etc. Slowly you see why a lot of people like fused deposition modeling over SLA or stereolithography. So real quick, a couple of housekeeping items. The show notes, like always, are at structural-md.com/P009. You can check them out there in my email. The slideshow, videos, photos, anything referenced will all be right there for you to take a look if you have questions or want to go back and look at something. So let's just jump right into it. You guys are busy people. No point holding you around. So the 140 character version of fused deposition modeling. It's a process in which a material is selectively dispensed through a nozzle or orifice. The filament is melted and extruded through the nozzle, and likewise parts are built layer upon layer as the build platform drops. So like a lot of things with 3D printing, there are synonyms or common terms that are used. So fused deposition modeling is also abbreviated FDM. It is also called fused filament fabrication, FFF, or that's probably going to sound super weird on the microphone, or F cubed. I just made those last two up to give you guys a little bit of a chuckle in your day. And then the last one is fused layer modeling or fused layer manufacturing, both abbreviated FLM. So the thing with the common terms, it's just something to kind of keep tabs on. Like most fields, we like to make up things or make things a little bit more complicated to make it seem like you have to be a professional in industry or a specialist when really 50 different words really mean the same thing. So how does the process work? Well, it's pretty simple. So it melts a plastic filament. It extrudes that filament through a nozzle. That melted filament is laid down on the build platform. It cools, it solidifies. The build platform, quote unquote, recedes or goes lower. And then layer upon layer is built, and then the part over time is built up. So like some other processes, this does require support structures, which anchors the parts to the build platform and then supports any overhangs or things of that nature that are going to fall due to gravity. Trying to lay melted material in midair. I don't know if you figured that out yet, but if you have, let me know. We might have a good business plan there. It's just another step in the post-processing. Like I've said, is the dark horse in 3D printing. A lot of people don't realize that it's not as simple as create, print, play with, if that's a good way to put it. There's a little bit of stuff that goes on between the print and the play. You got to post-process a little bit. The one nice thing is, though, the machine can have multiple extrusion heads, so you can use a second nozzle to be the support structure. It can be built from a different material if needed, and one that's easy to break away, one that is dissolvable in other materials. And another episode, when I say that I'll have an episode on it, part of it is, to be honest, a reminder for myself to make a note after I'm done recording to go back and mark down future episodes to make. So I will make an episode on slicing programs that kind of create the support structure that says where you need it, where it needs to be. So several parts can be produced at once with FDM, so long as they are anchored to the platform. So this is a hypothetical example. By no means are build platforms this big, but it gives it a good context for conversation. It makes math easy. So let's say your build platform is a cubic meter, so 1 meter by 1 meter by 1 meter. You can't build a part that fits within the XY direction, but it starts being built at 200 millimeters, so 2/10 of a meter in the air. Does that make sense? You can't just build a part in midair. It has to start somewhere on the ground, quote unquote. You can't defy gravity. But you can print in space. They're working on that. I'll have to do some more research on that one, but I have seen them trying to print stuff in space. So you can print multiple materials, or not multiple. Trying to say two different things at once with you guys. You can print multiple materials, and you can print multiple parts, so long as the parts are anchored to the build platform. There is no levitation printing. There might be. Talk to the guys that wrote Star Wars. There are also a couple of videos linked up for you guys in the show notes. I know it's kind of hard to put verbal context or verbally explain a very visually rich process, so check those out. They're not very long, just to kind of give a little bit more background into what I'm describing to you guys today. So the raw material is typically a filament of thermoplastic. It's coiled onto a spool that's melted and extruded. So basically you can kind of envision those large steel rolls or the telephone lines that are all wired up on a spool of a truck that they kind of run out as they string telephone cable or TV cable or internet cable between telephone poles. That's essentially what it is. I attached a reference table of plastics in the show notes. It's a very long, extensive list of different polymers that can be used, like ASA, ABS, PEEK, etc. The list is extensive. I'm not going to run through it. It can also do composites and wax materials as well. And then lastly, the really interesting thing is it can do viscous liquids or slurries. So what these could be are ceramics, composites, metal-filled clays, concrete, food, and living cells. This is the process that they typically use when you hear people print living human organisms, whether it's a liver or an ear. So they're loaded into syringes or a hopper, and then they're dispensed. But they don't need to be melted or change the phase of the material because they already are in that viscous liquid or slurry state, which is what you get when you melt the thermoplastic coil to run it through the extruder. The applications, prototypes, support parts, small series parts. So with the prototypes, it's typically form to fit and then functional testing with the standard material, so the plastic that's used with FDM. Support parts can be produced directly, whether they're jigs, fixtures, helps, and small series parts down to one of a kind that are built by standard materials. So again, this is like your consumer thing where they want to make something for their grandma, their mom, their aunt, their family member. It's a really one of a kind thing you can't get in a store, or you saw something funny, or you want to create something funny. That's what they would call a small series parts. For example, we're not going to discuss politics, but a lot of people did make political figurines of both Donald Trump and Hillary Clinton during the past presidential election. And that would be considered a small series parts. They were sold online at your quote-unquote pop-up shops. So on to the advantages and disadvantages. So with the disadvantages, let's look at the positive side first. So FDM can build fully functional parts in your standard plastics. Again, the list of plastics is listed in the show notes. FDM modeling works with standard materials like ABS or PC, so therefore the parts have a really good mechanical property and are pretty durable over time. The parts can be post-processed as any plastic part produced through a conventional method, whether it's a mold and die or something along those lines. And then onto the disadvantages. We have to cover them. Everything has one. Nothing's perfect. Through the deposition of extruded material layer by layer, the parts don't have isotropy in the Z direction, so the vertical. They have a step structure on the surface because you kind of see each layer. So I'm trying to think of a good analogy to put that in for you guys. Nothing's really coming to mind. I guess you could almost imagine it as when you're stacking cake layers on top of each other. Before you frost the sides, you can see the individual layers of cake, which is what you kind of see with FDM. Now, it's not to that extreme where it's that vivid, but when you touch it or you look at it up close, I'll be sure to put a picture in the show notes. You can see the step structure as the layers are laid and the build platform goes down and more layers are laid. So therefore, you can't get really fine details. And there's another reason you can't get really fine details that I'll touch on in the Additive Slices section. So in the Additive Slices section, likewise with all the other ones, these are figures that I can best get to date. They might change with time. That really just depends on businesses and them creating new printers. So the maximum build envelope for FDM is 914 by 610 by 914 cubic millimeters. Again, that's the maximum build envelope you can get. The minimum feature size, the typical tolerance, and the minimum layer thickness are all 0.178 millimeters. Do you know why that is? Take any quick guesses? Cue the Jeopardy theme song. So the reason it's like that is because that's really dictated by the size of your filament. So envision that as being the diameter of a pipe, for example. So the amount of water you can push through a pipe is really dictated by the size of the pipe. And likewise, the level of detail, the minimum feature size or thickness that you can get from an FDM printer is really dictated by the thickness of the filament you use. The thinnest filament sold that I could find was 0.178. Now that could change with time. As people change their printers or the market demands a difference, but that's essentially whatever your filament size is ultimately going to dictate your feature size, your tolerance, and your minimum layer thickness. Now those numbers can change, but they're always pretty much going to be the same unless someone figures out something that I'm not aware of. So there you have it. That is FDM, Fused Deposition Modeling. Again, the show notes, structural-md.com/P009. I'm more than happy to answer any questions you may have. More than happy to come speak at your company in regards to 3D printing, what it can do, just the limits, and really just provide a good basis, a good baseline of education for the people in your company. I'm more than happy to answer questions, whether it's can you explain this more? Can this application work with 3D printing? Anything along those lines. I'm an open book for you guys, so feel free to email me. I look forward to hearing from you, and until next time, have a phenomenal day.